Good afternoon, lovely people. I want to see more lovely people here. Could you please tell your buddies to show up? Okay. Last time we introduced the idea of continuous random variables and their probability density functions and cumulative distribution functions. So let me just quickly review those definitions. We introduced the cumulative distribution function, which actually can be applied more universally, not only to discrete random, continuous random variables, but also to discrete random variables. And if we have a random variable x, then the cumulative distribution function is the probability that that random variable x takes on values less than or equal to a certain amount, small x. And there's also a complementary notion to this, which sometimes is useful, and that's the complementary CDF, which is the probability that x is greater than a certain value x. And needless to say, these two values add up to 1. So FC is called the complementary CDF. We're not complementary. We won't really make use of this in this class, but I will mention it again in the context of Gaussian random variables, because some of the tables for Gaussian random variables are typeset in terms of the complementary CDF. You can't expect all engineers and mathematicians to agree on any notation, so there are some people who like less than or equal to, and there are some people who like greater than. Yeah, question? So for most of our the question was which one is better. The answer is it depends on the context and what you're reading and what you're more comfortable with. For the most part, we will stick with the regular, the CDF. Okay. Associated with the CDF, we found was, whoops, that's not what I want. I want an X, was the PDF, which we showed was the derivative of the CDF. And this is called the probability density function. And we also talked about how if we want to look at the probability that a random variable x is between some value small x and infinitesimally larger than x, this is given by f of x dx, because this would be the the CDF at x plus dx minus the complementary CDF at x. Remember, we're looking at the real line. We have an x and we have an x plus dx. The first term is the probability up to x plus dx. The second term is the probability up to x. The difference of the two is the probability that x is in this tiny interval. And we define the PDF in this way. So if you take the dx to the other side, you have f of x plus dx minus f of x divided by dx. Remember, the numerator is just the probability that x is in this interval between x and x plus dx. So what we're looking at here is probability divided by a unit of the random variable, and that's why we call this a density function. So that's why this is called a PDF. But that's the relationship between the PDF and the CDF. You can, of course, write the converse relationship, which is that the CDF can be obtained by integrating the PDF. I have to use a dummy variable here then. I'll use lambda, d lambda. So if I have some probability function, let's just say an exponential, then why is it that you don't take my... Then the integral of, so this is lambda, this is fx of lambda. The green area is the CDF. So you specify some boundary point. If you integrate the CDF to the left of that boundary point, you get the cumulative distribution function. Okay? So whenever you have a PDF, probability density function, and you want to figure out the probability that the random variable takes on certain values, you just integrate the PDF over that set of values. And whatever the area you get, that's the probability. Okay? Any questions? This is all review, except the complementary CDF. All right, cool. So let's go back to the black color. We talked about the exponential PDF, which was lambda e to the minus lambda x, and you know I like this unit step function, so let me define that for continuous variables now for you. Unit step function is the function that is 1 for x greater than or equal to 0 and 0 for x less than 0. I write it this way because I don't want to have to keep writing two cases, because otherwise I would have to say this is equal to that exponential, scaled exponential, and then it's 0 for that. So these are equivalent ways of writing the exponential PDF. And of course I drew it there. Let me redraw. It starts at 0, and the peak value is what? Lambda. You let x equal to 0, the exponential evaluates to unity, and you have lambda. And then it dies out from there. A lot of the systems in the real world that we deal with can be modeled well with the exponential. One of my favorite problems is light bulbs and their lifetimes. So if you model the lifetime of a light bulb as an exponential, and let's say you have a particular light bulb, and you put a brand new one, let it go all the way to its death, instantaneously replace it with another one, so you have a sequence of arrivals, if you will, where each arrival constitutes the death of a light bulb. It turns out that that's a very famous process called the Poisson random process. And it models arrivals, like I said last time, of packets to a router and things like that. So what is the... so last time we showed that this PDF integrates to 1. You won't have a valid PDF unless certain things are true. First of all, the PDF has to be non-negative for all values of the random variable, and it has to have unit area. So we showed last time that the area under this exponential is 1. Now what I want to ask you is to figure out what the mean is of this random variable. The mean, just like the discrete case, is a weighted sum of probabilities, except our quote-unquote, air quotes, sum is an integral. So this is the definition of the expected value for a continuous random variable. This thing here is the quantity analogous to px of x in the discrete story, and this integral is analogous to the sum over all x. Okay? So If you understand the formulas in one realm, you really don't have to memorize new stuff. Sums become integrals, and probability mass functions become the density functions times dx. Okay, so what I want you to do is work with your neighbors and figure out what the mean of this random variable is, and give me the answer. I'm trying to get you to de-rust some of your integration talents. Yes, you will need them in life. Life is continuous, unlike what they teach you in Soda Hall. Contrary to what they teach you. What technique do you invoke to solve this problem? Integration by parts. So I hope nobody's banging their head against the wall trying to figure out how to do this integral. Can you help me with the limits? Rohan. I'm competing with you, my man. You were wearing bright the other day. I figured, I should come into the play. Go for it, Rohan. What are the limits? 0 to infinity. And then what do I put here? X. Times what? Well, give me what to write. Lambda comes out. E to the minus lambda dx. Okay? So you said integration by parts, people. What's u? X. So then du is dx. And what's dv? Okay, that's fine. We use lambda e to the minus lambda x dx. So v is? So if we're going to do that, let me just keep the lambda inside the integral then. I'm going to put x and put lambda here. Okay? So this is my v, and that's my u. So v is what? Negative e to the negative lambda x. Okay? Is everybody here? Physically, mentally, spiritually? So uv is minus. Rohan, my man. Talk to me. Okay. Can you pretend like you're in a basketball court and you're rooting for your team when you're talking so that the people on the other side can hear you? No. Oh, that like that. Okay, come on. People are going to walk in and wonder, well, who's this nut job who's teaching this class? I apologize to you folks. Yeah. And then you evaluate that from 0 to infinity. There we go. Getting better. Well, we have another term. Hashtag second terms matter. Especially in presidential elections. Be sure to vote. Do I have a plus or a minus? I got a minus, so it's uv minus integral v du, no? So I've got a minus here and I've got a minus here. Yeah, we don't want minuses here. Minuses are bad. 0 to infinity. du is not 1. du is dx. E to the negative lambda x. So, what's the first term? When x is infinity, what's happening? How about I rephrase the question? If I take x toward infinity, this x grows toward infinity, right? What does the exponential do? It goes toward 0. Which one dominates? The guy who grows linearly toward infinity or the guy who dies toward 0 exponentially? Exponential dominates. So at infinity, this term is 0. Minus minus is plus. And then at 0, what do I have? The exponential evaluates to what at 0? 1. And the x evaluates to 0. So I've got a 0 plus 0 situation here. Now, is there a smart way of not having to do the integral and yet evaluating that integral? This is a question to everybody. Can I do this quickly based on something we did in the last lecture? What do you know about the exponential? Back there. I multiply by lambda. Let me put that in a different color here. I multiply by lambda and I divide by lambda. Now the integral is what? What am I doing when I'm doing this integration? So I've got this 1 over lambda sitting outside. And what is this? It's 1 because it's the integral under the exponential PDF. We've already figured that out. Remember the mathematician's joke? You convert it to a problem that you've already solved before. And this is 1. So the mean of the exponential is 1 over lambda. Don't do extra work when you don't have to do extra work. Okay, courses like this are not about how much time you put in. It's about how efficiently you work. So you want to develop those skills that make these kinds of things jump out of the page at you. Okay. I'm going to leave it to you to figure out what the second moment is, and from there to show what the variance of x is. So the second moment is also going to involve integration by parts, and I'm going to leave these for you to do on your own. So it gives you the same kind of practice I just gave you for the mean. All right? And the other thing I'm going to leave for you is to figure out what the CDF is for the exponential. How about you help me set up the integral, and then you can do the integral on your own. What's the integral? It goes from where to where? The definition says what? From what? Negative infinity to x of the density. Right? So in the case of the exponential, what's the lower limit? Louder. 0 to x of lambda e to the minus lambda x dx. Okay? Oh, yeah. Oh, bad. Okay, thank you. Bad notation. Here. Pick another Greek letter. T? I don't know if the Greeks will appreciate you ascribing the letter T to them. Maybe tau? Tau. So we'll do, and that's tau. D tau. There we go. Now it looks good. So, whatever function you get had better go to 0 on the left as you go toward minus infinity, and go toward what on the right? What is the CDF approach? 1. Okay, so this is another exercise I'm going to leave for you. These are all in standard books, so it shouldn't be difficult for you to verify your answers. But it gives you some integration practice. Get comfortable with integrating exponentials. Yeah? Oh, I'm sorry. This equality with the triangle sign means definition. So by definition, the cumulative distribution function is what's given on the right-hand side. Okay. So that's that. And I'll skip over the uniform. Let's take you to some exciting realms. Here's a random variable z, whose PDF is given by this guy. What does this function look like? Have you seen this before? Have you been pained by this before? Especially on exams. What do you think it looks like? It's a normal distribution. Notice it's an even function. It's even in z. It peaks where? Where is the peak of this function? Everybody. 0. And then as I go toward infinity or minus infinity, doesn't matter which direction I go, it's an even function. It decays. Okay? So it's centered at 0. And the value at 0 is what? 1 over? I can't hear you. Square root of 2 pi. Okay. And we talk about a certain thickness of this PDF. It turns out to be 1. And that's the standard deviation of this random variable. This is called the standard normal random variable, or the standard Gaussian random variable. Okay. What can we say about this random variable? You told me already that the mean is 0. It turns out the area of this function is 1. I'm going to do a poll. Do you want us to show that the area is 1? Or are you happy to just accept that the area is 1? Talk to your neighbor and see what you want done. I'm going to make this a quasi-democracy here. What's the verdict? Yes. No. What if I tell you we need multiple integrals to do that? Yes. What a bunch of self-flagellating individuals. No. I can't believe the yeses win. Wow. Remember that 1-800 number? What was that? What was that 1-800 number? Get life. Okay, we'll do it. All right. First, I'm going to get rid of a calculus preliminary. And that calculus preliminary is that the integral from 0 to infinity of r e to the minus r squared over 2 dr is 1. How would you do that? Prove it. Can you tell me if this function can be written as the derivative of something else? It's d over dr of what? Nobody? Negative e to the negative r squared over 2. If you differentiate that, don't you get the integrand? Is everybody here? Chain rule. I differentiate the exponent. That's minus 2 divided by 2. So that's minus 1. That's why we need another minus here. And then e to the, and then what? 2r. That's where the r comes from. And then you've got the exponent. So then you have 0. So the integrand is minus d over dr of e to the minus r squared over 2 dr. So this is minus e to the minus r squared over 2 from 0 to infinity. And what does that evaluate to? At infinity, it's what? What is this exponential at infinity? 0 minus another minus plus, and at 0 it evaluates to 1. Okay, we're done with that preliminary. I'm going to make use of this a little later. So, I'm going to define the integral of the PDF, which I'm trying to show as 1, with this capital letter I. So this is from minus infinity to infinity, e to the minus z squared over 2 dz. That's the area under the Gaussian, standard Gaussian. Okay? I'm going to square this. And we'll show that the square is 1. If I want to square this, then I need two variables. So 1 over square root of 2 pi becomes 1 over 2 pi. And I have an integral. I'm going to express this I in terms of two different variables, x and y. So I have a double integral e to the minus x squared plus y squared over 2 dx dy. It's as if I've written this I in terms of x, and I've written it again in terms of y. Because I'm multiplying two of these integrals, I need to have separate variables for them. And this, of course, goes from minus infinity to infinity for each of them. Okay? Now, we have to convert to polar. Hey, I gave you an option. Do you want to stop? Stop. Don't stop. Oh my God. Never a dull moment in teaching at this university. So we convert to polar coordinates. In rectangular coordinates, you've got a dx and a dy. So that's what this is. So this is your infinitesimal area of integration. What we want to do is go into polar coordinates. So I have a radius r. I go infinitesimally above it and infinitesimally below it. And so instead of a dx and dy, I'm going to go radially. So when I go radially, I've got one dimension, which is the radius, and I've got another dimension, which is the angle. So instead of the x and y, now I have variables r and theta. Can somebody tell me what this arc length would be? Let's pick red. What is this arc length here? Why is this not showing up properly? Oh, I'm sorry. This is not theta here. This is d theta. We're dealing with this is d theta. This is a very tiny angle. Just like in the dx dy, I've got infinitesimally small in this direction, infinitesimally small in this direction. In radial coordinates, in polar coordinates, I've got an infinitesimally small radial dimension and an infinitesimally small angular dimension. So what's the length of this red arc here? Yeah. R d theta. And if you're not convinced, think about how when you go around and the full circle, it's 2 pi radians, and the arc length is what? 2 pi times, on this radius r, if you go around the circle, what's the length you traverse? What's the circumference of a circle? 2 pi r. So when you go through a d theta, you get this length. Okay? That's basically where this red length comes from. So it's 2 pi r over 2 pi d theta over 2 pi. It's basically a proportional relationship. Now you tell me how you would write. So in the rectangular coordinates, the area of this infinitesimal region over which you integrated was dx times dy. Can you tell me what the corresponding area is here? Yeah, you can assume that that's a rectangle. The length is r d theta. And the width of that rectangle is dr, no? Because I want dr over 2 above and dr over 2 below. So that's how you convert to polar coordinates. So my I squared is 1 over 2 pi. Integral. E to the what? What's the exponent now? So my r squared is x squared plus y squared, no? I'm going radially. So what's the exponent? R squared over 2. And then I've got r dr d theta. Okay. What's the range for theta? 0 to what? 2 pi. Remember, I'm trying to cover the entire two-dimensional plane with r and theta. So angular-wise, I go around a circle of 2 pi. So that's 0 to 2 pi. And the radius goes from where to where? 0 to infinity. Excellent. You must have had a very fun moment earlier in this lecture. Now I can separate these two integrals because I don't have any terms that mix theta and r. So what's the integral in terms of the theta? I'm integrating d theta from 0 to 2. I'm integrating the number 1 from 0 to 2 pi. What does that give me? So it gives me 2 pi. And then I'm left with 0 to infinity, r e to the minus r squared over 2 dr. And what did we just say earlier? This evaluates to 1. 2 pi over 2 pi, 1, 1. So I squared is 1. I squared is the integral of this function. So I is non-negative. I is the integral of this Gaussian function. It's non-negative. So if I squared is 1, and I know I is greater than or equal to 0, what does that say about I? 1. We're done. They do teach some useful stuff in Math 53. But you don't need the entire torture to make sense of what we're doing. Okay, so the Gaussian we've shown integrates to 1. Excellent. So this function is a valid PDF. It's non-negative, and it integrates to 1. Beautiful. Yeah. No, you don't. That's why I gave you an option. I would not expect you to do any of this multivariate stuff on an exam. If we ask you to find the probability on a two-dimensional plane with joint variables, then it would be very simple to do without having to do actual integrals. Yeah, don't freak out, please. You can blame your classmates for this segment. Okay, using integration by parts, you can also show that the standard deviation of this PDF is this random variable is 1. I'm not going to go through that because we've already done more grunt work than I normally like. So let's just write down the salient features. The expected value of z is 0. You don't have to do any work for this, huh? Well, other than actually writing minus infinity to infinity z 1 over square root of 2 pi. This is the definition, right? The definition of the mean. E to the minus z squared over 2 dz. What is it about this integrand that allows you to say immediately that this mean is 0? It's what? It's an odd function. E to the minus z squared over 2 is even. When you multiply it by z, you get an odd function. You're integrating an odd function from minus infinity to infinity. You must get 0. Okay? The other way you can argue is more heuristically, which is that the mean, we said, was the center of mass, or the center of gravity of this density. And clearly, by symmetry, that center of gravity is sitting right there at 0. Okay, each of those is perfectly valid if you make that argument. Now, when the mean of a random variable is 0, remember that the variance we found was e of z squared. Well, actually, that's not the definition. That we found that to be the case. Minus e squared of z. This you've already shown is 0, the mean squared. So anytime you have a 0 mean random variable, the variance is the same as the second moment. So to find the second moment, you would have to do the integration with not a z here, but a z squared. That would involve an integration by parts. We've already done enough of that this lecture. I'm going to leave that for you to figure out. So this you can show, again, just to get the practice, it's good for you to go and show that this is equal to 1. Okay. Can I scroll up? Or scroll down? Huh? Or scroll up? Whatever. This Gaussian random variable has a whole bunch of really awesome properties, but there's one thing really ugly about this random variable, which is that its its CDF, which is 1 over square root of 2 pi, minus infinity to x, e to the minus z squared over 2, this is random variable z, dz. So the area under the Gaussian from minus infinity to x, so this is the Gaussian, z, This has no closed form solution. There is no expression you can find that gives you that area in a clean way. And that's why we're stuck with tables. Okay, so this is a table of... Wait, why is this so... How do I zoom out of here? Well, you don't actually have to see the whole thing. But basically, this is what you would need to figure out probabilities with the Gaussian. Now the good news, so that's the bad news. The good news is, for all other Gaussians of different means and different variances, you don't need a separate table. There is a transformation that takes you from the standard Gaussian to another Gaussian of an arbitrary mean and arbitrary variance. And you can convert the probabilities involved with those other random variables, all belonging to the Gaussian family, by knowing or by having access to these values, whether by software or on an exam. Obviously, we would have to give you a table. So, here's where there's some difference of opinion as to what's more convenient. I belong to the camp that likes the cumulative distribution function, but you will find many engineering texts and computer science texts where they like the complementary CDF for the Gaussian, and the table they give you is for the complementary CDF. You have to get comfortable converting one from the other. But that's basically what we're up against. So if I'm looking at the probability, the CDF at 0, what should that value be? Even without looking at the table. What's the probability that this standard Gaussian random variable is less than or equal to 0? 1/2. And that's exactly what the table says. See, 0, 0, 0. This is just additional digits of accuracy. So you see a 0.5 there. All right. Now, what is the probability that... So here's my question to you. Let's look at that table. And you tell me the probability. See if you can work together and figure these probabilities out. Here's 0. Here's 1. Here's -1. Can you tell me what the probability is that you're within one standard deviation? Yeah, sorry. Let's go here. I'm talking to myself. What's the probability that if you're looking at the standard normal, you're within one standard deviation of the mean? Okay? Draw this figure. I have to switch to the lectern. So this is your... this is FZZ is 1 over square root of 2 pi e to the minus z squared over 2. Now let's switch there. You tell me what that value is. What would you have to do? You can't just read the value from the table. What would you have to do? Actually, let's go back and determine the strategy first. So I'm interested in this probability that z is between 1 and -1. I can put an equality here as well because there's no probability sitting smack at -1. But what's the probability that I'm within one standard deviation? Can you express this in terms of the CDF? Don't Google it. Sheesh. Just look at the diagram. What do I have to subtract from what? F at 1, and I subtract from that f at -1. But the table doesn't give me f at minus 1. So how do you figure out f at minus 1? Look at this. Table doesn't give you any negative values. So talk to me. What is f at minus 1? F at minus 1 is this area, correct? Let me. F at minus 1 is this area, right? F x at minus 1. How do you figure that out? Yeah. But the area from 0 to 1, yeah, you can do that. So it's 1/2, which is the area all the way to 0, and then you subtract the area from 0 to 1. But the area from 0 to 1 itself requires a difference of 2 values. When you look at this symmetric function, yeah. Exactly. We do 1. So notice this pink area here is the same as this black area here. No? And what is that black area? That's the complementary CDF. At where? 1. So this is, and the complementary CDF is simply given by 1 minus that. So I have fx at 1 minus 1 minus fx at 1. And that gives me 2fx at 1 minus 1. Now we go to the table. Is everybody here? I'm using the symmetry in the Gaussian to figure out areas that I'm interested in. I want to figure out the probability that I'm within 1 standard deviation of the Gaussian. Let's go to the table. All right, now you tell me what that calculates to. What is fx at 1? 0.8413. Is that true? Yeah, it's right here. Wow, my hand looks really scary. It's not that scary from here. Okay, so it's that value right there. See that? So what is can somebody run this through a calculator and tell me what you get? 0.6826. So the probability that you're within 1 standard deviation of a Gaussian is roughly 0.7. Okay? And you can do this exercise for 2 standard deviations and 3 standard deviations. By the time you get to the 3rd standard deviation, pretty much all of the probability is sitting there. People who do trading in the markets would disagree with you about those tails. Those tails can have blown the accounts of many a trader in the financial markets. But anything that happens beyond 3 standard deviations really is, you can think of it as a black swan event. So if you've ever heard of the term 6 sigma, when somebody's 6 sigma out, it's usually in reference to this Gaussian. You're 6 standard deviations above or below everybody else. Okay. Oh, I was talking to myself again. There we go. So those are the numbers. So 2 times fx at 1, we read that off the table, and we subtracted. Okay? I will give you a PDF file of this table so you can play around with this. Or you can just download it from anywhere. It's universally available. Any questions so far? We will come back to the Gaussian when I talk about the central limit theorem and the law of large numbers and so on next week. Yeah.
Can computers efficiently calculate the cumulative distribution?
Yes. So computers can actually do that integral numerically. That it can be done. Yeah. That's how these tables were created. Yeah. So you can actually program. Yeah. We will give you the table if there's a problem on the test that requires you to look at the table. Yeah. You don't need to bring a table with you. We'll give you a copy of the table. Okay. All right. Now, I want to talk a little bit about a topic that's sometimes referred to as derived distributions. And sometimes referred to as distributions of transformed random variables. It sounds scarier than it actually is. I'm going to start with the linear case. So I have a random variable, I'll call it z. I've got a random variable z. It's got some PDF that governs its probabilistic behavior. And I define a new random variable, y, which is alpha z, let's make it sigma z plus mu, where sigma is a real number and mu is a real number. They're deterministic. And I'm interested in the density for y. Okay? If all I ask you is what's the expected value and the variance of the random variable y, you don't need the density for y to answer that question. What is the expected value for y? So if z has mean, let's say, so let's just to keep the mean Ez and variance sigma z squared. What's the expected value of y? What do you know about this expected value? This is not, I don't want you to interpret this as standard deviation just yet. This is just some quantity, and it may even be negative. And this is some other quantity. So what happens to the sigma and the mu in this expected value? What property of expected values do I need? Linearity. So linearity says this is equal to what? Everybody. Sigma E of z plus mu. And what about the variance of y? That's a little trickier, huh? What about the variance of y? Does the fact that I'm adding a constant to this random variable here change the variance? So I had better not have any mu in the expression for the variance of y. So how does the sigma affect the variance of y? Work with your neighbors. We didn't do this explicitly in class, and apparently they didn't do it in discussion. When all else fails, go with the definition. Definition says this is what? The expected value of what squared? By definition, this is what? No, just give it to me in terms of y and e of y. Y minus e of y. Quantity squared. That's the definition of the variance. And when you work it out, so what does that look like? Y has an expression. Sigma z plus mu minus what? This is y, no? What's e of y? We just figured that out. Don't be shy. I'm not asking a trick question. Talk to me. Sigma e of z plus mu, but there's a minus in front of the whole thing, so it's minus mu. What happens to the mu's? They go away. The mu goes away. You don't want any mu floating around in your expression. Okay, so now I have, give me my black back. So I have I forgot the expected value here. Expected value of sigma z minus sigma e of z quantity squared. How would I massage that to get what I want? You factor out? So the sigma comes out of this, squared, and then, can I take it outside? Okay, so I have a sigma squared, e of, what squared? Z minus e of z. And what do you know about this? What is that by definition? Variance of z. So the variance of y is sigma squared times the variance of z. So remember where we started? We started with this. Y is a linear function of z, and we found that expected value of y is simply the expected value, not the expected value of z. It's sigma times the expected value of z plus mu, and the variance of y is sigma squared times the variance of z. Scalar multiples of random variables produce new random variables whose variances are according to the square of that scalar multiple. So if I'm multiplying z by sigma, the variance is the square of that multiple. That's all you have to remember. Okay? So this is important. And we haven't even gotten to the density yet. Any questions on what we've done so far? So we can do all of this stuff. We can talk about the first and second order statistics of a random variable without going into the density of the random variable y. But now I want to know what the density of the random variable y is. But what about fy of y? I don't need any quotes. Okay. Now, I'm doing this topic of derived distributions using linear functions of random variables, but the method is much more general than this. The foolproof way of doing this is to first figure out what the CDF is, and then you use the fact that the density is the derivative of the new random variable to figure out the PDF. That's the method that will work whether you're dealing with Well, regardless of what kind of random variable you're dealing, continuous random variable you're dealing with. So, for linear functions, there are other ways of doing this, but they can't be generalized to arbitrary functions of z. So, this is the probability that y is less than or equal to y, correct? That's the definition of a CDF. What does that say about z? What is z? If y is less than or equal to y, it means this expression is less than or equal to what? Y. Which means z is less than or equal to what? Now that's an equality from middle school. Y minus mu over sigma. Isn't this thing on the right simply fz at where? Isn't this in the form of the CDF for z? Yes or no? Okay, but what's the argument? My small z here is whatever's on this side. Okay, so now we have a relationship between the cumulative distribution for our new random variable and the cumulative distribution for sigma. I have made an assumption here about sigma that went right past you. That it's what? Well, it had better be non-zero, but one more assumption. It's what? Positive. So I've assumed this is positive. Assume. You can rederive this for negative sigma as well. But the one that's useful for us is positive. Because if sigma is not positive, then when I go from here to here, I have to change the direction of the inequality. So assume that sigma is positive. Now I have a relationship between the CDF for y and the CDF for z. So what's the PDF for y? Isn't that just the derivative? So on the right you have a function of y. On the left you have a function of y. To get the density, what am I doing to each side? Everybody. That's not everybody. You don't have to say it 5 times. Everybody. Derivative. Okay. So when I differentiate this function of y, what do I get? What does chain rule tell you? D over dy times what? Times what? Oh boy. See, that's why I think they should require Math 1A of everybody. You guys come in with this AP credit, then you get stuck here. Mr. Rogers didn't teach you that stuff in AP Calc. This is the derivative of this guy times, well, the derivative of capital F is this guy. And what's the derivative of this fraction? 1 over sigma fz of y minus mu over sigma. Okay? What does this mean for the Gaussian, for example? So this is what we found. Fz y minus mu over sigma. That's what we found. So let's say z is the Gaussian. By the way, we have some shorthand notation for Gaussians. This is one way we say z is a standard Gaussian. The script n stands for normal, 0 mean, unit standard deviation. Another way we can write this is by saying this is equal to, then we give the variable, 0 mean, unit standard deviation. And that's this expression here that we've already seen. So if Z has this density, and Y is equal to sigma Z plus mu, can you tell me what the density for Y is? First of all, there's a 1 over sigma, correct? So I just multiply whatever expression I have here by 1 over sigma. So I have 1 over sigma, square root of 2 pi, and e to the minus what squared? Y minus mu over sigma. That whole thing is squared, then divided by 2. Well, if I work that out, it's going to be 1 over sigma square root of 2 pi, e to the minus y minus mu squared over 2 sigma squared. This is the general expression for a Gaussian random variable that has mean mu and standard deviation sigma. Why? Well, if Z has 0 mean, what's the mean for Y? Z has 0 mean, so what's the mean for Y? You don't even need the PDF to determine that. What's the mean for Y? It's mu, because we just said the expected value is linear, and this is 0. So the mean is mu. So you're looking at a Gaussian that's centered at mu. And Z has unit variance. What's the variance for Y? Didn't we say it's the square of whatever this scaling quantity is? Didn't we just derive that? So it's sigma squared, which means the standard deviation for Y is simply sigma. So I'm looking at a Gaussian with standard deviation sigma and mean of mu. This is how we create every single Gaussian in the Gaussian family. The Gaussian, the monarch of them all is the standard Gaussian that has 0 mean and unit variance. You just need one table for that. And you can figure out all the other probabilities with this linear transformation. Yeah?
Why is there a negative z squared over 2 in the probability density function of the standard Gaussian instead of just e to the negative z squared?
If you don't have, so the question is, why do you have the z squared over 2 in the exponent and not z squared? If you don't put the 2 in there, then the standard deviation will not be 1. So it's there to make it 1. And we keep it for all the other Gaussians. So we write Y is a Gaussian with mean mu and standard and variance 1. Or we write Y is like this, and we write the density in full expression in this way. Y minus mu squared over 2 sigma squared. Notice the mu that we're subtracting from the y in the exponent and then squaring make this function even with respect to, or symmetric with respect to the point. Y equals mu. So now if I want to figure out the probability that some arbitrary Gaussian is less than or equal to y, what I can do is, first, I subtract the mean for y from it, and then I divide by the standard deviation. This function of y has what kind of a mean? 0 mean. If I take the expected value of this quantity, so expected value of y minus mu over sigma is, the sigma comes out, and I have expected value of y minus its expected value. So this is clearly 0. What's the variance of this quantity? It's what? Sigma squared? It's 1 over, the mu doesn't matter, right? The subtraction from this constant doesn't matter. So this is the same as variance of y over sigma minus mu over sigma. Subtracting a constant value or adding a constant value to a random variable or from a random variable makes no difference with the variance. What makes a difference is the scaling of that random variable. So this is 1 over sigma squared times the variance of y, correct? And what is the variance of y? Sigma squared. So I have standardized the random variable y. By doing what? By subtracting its mean and dividing by its standard deviation. So now I have transformed the probability, the CDF for y, the probability that a non-standard Gaussian random variable is less than or equal to small y, into the problem that the standardized Gaussian is less than or equal to this value. And for that, I have a table. Right? So that's why you don't need different tables for different Gaussians. Any Gaussian that you have, to figure out the probability that it's between two values or less than some value or whatever, you convert that Gaussian into a standard Gaussian, and then you look up the table or plug it into whatever software or calculator. So the probability that some non-standard Gaussian is less than or equal to a certain amount is the same as the probability that the standard Gaussian obtained from subtracting the mean and dividing by the standard deviation is less than that amount. Okay? So that's why one table does the job for all cases. And the table is not tabulated for negative values of the argument. It's tabulated only for the positive values because you are also expected, as an additional layer of fluency, to exploit the symmetry or the evenness of the Gaussian. Yeah, question? Usually it's denoted with, so the standard Gaussian usually we use the letter Z. And I don't know what you mean by notation, but so for non-standard, we say and y is normal with mean mu and variance sigma squared. For standard, we say it's mean 0, variance 1. Yeah. Okay. Now, I don't know why this is not erasing. What is your problem? Okay. I'll start another topic, and then we'll have to develop it next week. Joint PDFs. So we talked about linear transformations of random variables. Now I'm going to bring in more than one random variable. A joint PDF you can think of pretty much the same way you thought of joint probability mass functions. I have two random variables. They can take on values x and y. And I want to talk about the probability. So just as I had joint PMFs, I want to talk about joint PDFs. Let's say this is x plus dx, and this is y plus dy, and I've got a function sitting on this plane. Okay? So the joint PDF is a function sitting on top of this plane. In the one-dimensional case, when you multiplied the PDF with dx, you got the probability that capital X was between x and x plus dx. Here, you're just expanding it to more than one dimension. Let me erase this here and just make it shorter. So this is the same as the probability that x is between x and dx, and y is between y and y plus dy. Okay? So I'm looking at this area. And the joint density is that probability sitting over that infinitesimal area. So it's this probability that we just wrote up there. Blah, blah, intersection with blah, blah, over dx, dy. This is called a joint probability density function of x and y. I'm going to set up a problem. Let's make this a page turner. I'm going to set up the following problem. A French nobleman by the name of, he's known as Buffon. And last summer, I happened to be in Paris, and I noticed Parisians really like this guy. There's a street named after him in Paris. So he posed the following problem. You have a plane that is ruled by these straight lines. The distance between these straight lines is d. So this is called Buffon's needle problem. I hope that was his only problem. So imagine this infinite plane ruled by these lines that are parallel of length d. And you have a needle of length L. So there is a needle of length L. That you randomly toss on this plane. L is less than or equal to d. Okay? What is the probability that the needle crosses a line? We will solve this using joint PDFs next time. Okay, that's the setup. Is that clear? The needle can't cross two lines because of the way we've set up the problem. But we're gonna solve this problem next time with joint PDFs. Have a great weekend.